session. So it is my pleasure to introduce the next speakers. So we have Sergi Parareda and Andoni Agirre from Gestamp, and they will be representing the Flexcrash project. Their presentation title is Flexcrash, New Generation of Crash-Tolerant Structures. So I'd like to say a few words about our presenter. So Sergi is a PhD candidate in material science, and he has a research career at Eurecat since 2015, including a short stay at the Scania Research Center. So his main area of expertise covers the intricate fields of fatigue and fracture behavior of metallic alloys. And Andoni's professional career started in 2015 as a CAE engineer at Gestamp R&D in Paris, developing projects for the main French car manufacturers. And since 2022, he has been involved in OEM and other R&D projects worldwide as a product engineer based in Spain. So within this position, Andoni contributes to the design of components based on Gestamp's technologies and highly engineered products focused on weight, CO2 footprint, cost, and safety parameters. And his academic background includes a master's degree in mechanical engineering from the Faculty Engineer of Bilbao and a master's degree in aerospace propulsion from Cranfield University. So my pleasure to give the floor to you both. Thank you.
Thank you, Carla, for the introduction. I hope you can see my screen, the presentation in full screen. Perfect. Yes, well, as mentioned, today we will present together with Andoni the Flexcrash project. Here you can see an overview of this presentation. So the aim is to cover a lot of different points, but mainly just the introduction of the Flexcrash project, the needs that the project will try to solve, the research beyond the state of the art, some fresh results that we have since it's let's say a quite new project, and then some work that we already done in the different work packages. So the Flexcrash project, just to have an overview, is a no-reason project that have a duration of 4 years and started last year in 2022 with a budget of 4 million euros. And we are 10 partners from 5 different European countries. And we are coordinating this project from Eurecat. So the main, and here you can see in the slide, the main aim of this project is to develop these crash-tolerant structures by using green aluminium and also by developing these new hybrid manufacturing processes. So regarding the consortium, we are 10 partners, as I mentioned, from 5 European countries, from Spain, Sweden, Italy, Austria, and Germany. 3 research centers, which are Eurecat, Fraunhofer, our virtual vehicle, 2 universities, Luleå, IMC, 3 industrial partners, GMAT, Gestamp, and Aerobase, and 1 industrial research center that belongs to Stellantis group, and then the standardization body from UNE. So regarding Flexcrash, the main, as I mentioned it very briefly, the main aim of or the main idea of Flexcrash project is to help the automotive sector, which is, let's say, sometimes quite traditional when dealing with this manufacturing of steel metallic parts, let's say. And the main aim is to develop new flexible and hybrid technologies that will help to obtain a crash-tolerant structures, and mainly made of green aluminum alloys. And to obtain these crash-tolerant structures, the project is focused on developing new surface patterns on some points of the vehicle, some strategic points of the vehicle that will help to reduce the weight of the vehicle, of the new components, but also to increase the safety of the vehicle, and of course reduce the risk and fatalities in crashes. So with these different points, the main the Flexcrash project will contribute to the European automotive industry by obtaining a more sustainable and lighter vehicle structures So as I mentioned, by using these green aluminium alloys and these new techniques, we'll be capable of obtaining these new lighter structures that will perform much better in crash situations. This point will help to achieve the European Union emission targets. So by reducing in 40% the greenhouse gases by 2030, which is also aligned with the European policies for a cleaner and more competitive Europe. So the main aim, as you can see here in the right-hand side of the slide, is to obtain low weight components that can perform better in terms of crash, but also that can help to reduce the CO2 emissions, while the greenhouse gases of the vehicles. So in order to achieve these 2 points, basically we are facing two different, let's say, two different points. Which one is the vehicle lightweighting. So the main aim is try to reduce as I mentioned, the weight of the vehicle, and the other one is to increase the passenger safety. And these are the main points of the project. So the project is mainly focused on working in this area, and the expected results after working on developing these different points were expected to be the crash simulation from advanced material to virtual testing. So cover all the chain, let's say, from the very beginning, identifying which are the most critical situations in crash scenarios, and then working on the different materials and different solutions that we can bring to deal with these situations. Then work and obtain these flexible and hybrid manufacturing technologies to bring to the automotive industry another tool to address the new requirements that can appear in the future. Obtain these new crash tolerant structures with lighter vehicles as well, and then also work with advanced testing. So the main idea is to develop new tests to obtain or to characterize the materials that we are using in terms of crash, toughness, fatigue, a lot of different mechanical properties in a fast way. So in this way, we can just increase or reduce the time required to implement all of this knowledge that we are developing here in this project. And finally, so related with the first point, just identify the current needs in terms of safety, but also the future needs that will appear when we will have these autonomous vehicles and also the conventional vehicles, let's say, and what will happen in these scenarios. So here we have just very schematic the project phases. So we have a first phase, identifying this crash situation, gathering a lot of information of which is the current situation and the future situation of the crash scenarios, and then improving the crash simulation in order to predict which will be the injuries of the passengers or the most probable situations in case of crash. And then in the phase 2, develop new materials and new solutions in order to give an answer to these different situations identified in the first phase. And finally, virtual and experimental validation of all of these different solutions, just to validate that we are solving this in the proper way, the points that we identified in the first stages. Okay, and now here I will just to share with you a short video about Flexcrash to have an overview of Flexcrash. I hope that you can listen it properly. If not, we will share with you the link of the video, and you can then
Road crashes are a serious concern for everyone who gets behind the wheel. And while the European Union aims for a 50% reduction by 2030, progress towards this goal has been slow. The Flexcrash European project takes on this challenge to transform the automotive sector. Flexcrash is dedicated to developing flexible and hybrid manufacturing technology that produces crash-tolerant vehicle structures. At Flexcrash, our focus is on designing safer vehicle structures by locally reinforcing critical areas in a crash event. This approach increases passenger safety and reduces fatalities across a wide range of crash conditions. By seamlessly integrating high-strength green aluminum alloys into its car structures, Flexcrash achieves both lightweight and sustainable chassis, maintaining their impact resistance and minimizing their environmental footprint. To ensure that Flexcrash structures meet the safety needs of current and future mobility, they will undergo rigorous testing, which includes advanced material models, different crash scenarios, and virtual testing. An initiative supporting the EU long-term goals on zero emissions mobility, reduction in injuries and fatalities due to crashes, towards safer and lighter crash structures. The Flexcrash project has received funding from the Horizon Europe program under.
Okay, so now I just leave the floor to my colleague, Andoni.
Thank you, Sergi, for this complete introduction. So now I will try to give an overview of the work that has been done in this first year of the project. But before explaining the concept that we have started to work on, I would like to shortly talk about the future relevant crash scenarios, because this is only a key point of this project. So in this sense, what we can already see in the roads is that the traffic is more and more heterogeneous. We can see at the same time in the same road traditional combustion cars with fully electric vehicles. We can also see bigger and bigger SUVs with small city cars. And what we know is that this trend will continue to increase in the future as automated vehicles massively start to share the roads with the human drivers. So this is, in fact, one of the objectives of the project, try to identify how this mixed traffic environment in the future can affect the crash events compared to the current situation. In this sense, we can expect less human errors, so we have some ideas, but the information and real crash data available related to automated vehicles so far is quite limited, with a few experiences worldwide. So this is why in this project, our project partner, IMC University of Krems, has developed a tool that reconstructs crash scenarios based on genetic algorithms, and that allows us to simulate how an automated vehicle would react in a real crash situation. So for this purpose, this tool takes as a input existing real crash reports, and based on this, it generates and it optimizes a crash scenario, a simulation. So once the simulation is set up, we can place the autonomous driving system into the simulation and see how it reacts and which is the consequence of this collision, so that we can get as an output all the relevant collision metrics, such as the impact angle, the velocity, the location of the collision, and so on. So if we move to the following slide, if we what we have done is we have cross-checked the output of this tool with the benchmark, and we have identified three main scenarios, crash scenarios for this project. So the first one on the left is the straight crossing path, where we can see the blue car going straight, that it's impacted from the left side. The second one, which is a left turn across path, in this case in lateral direction, because the blue car is turning left. And the third scenario that we have identified is also the similar to the previous one, but in this case it's in opposite direction because the green car is coming from the front. So if we move on one slide more, we have already identified the crash scenarios that we will use, but now the goal is to design a structure that can absorb enough energy in a frontal crash so that we can avoid any kind of injuries on the occupants. So this statement is quite clear and quite simple, but all the implications behind are quite complex because we need to take into account legal requirements and the protection not only of occupants but also of pedestrian, many variables in terms of speed, in terms of impact angle, overlap, proportion of overlap between different cars, compatibility, and of course, economic factors that we always need to keep in mind, and sustainability and ecological factors that are fundamental in this project. So in order to achieve this goal, we have combined, or we're going to combine three pillars. On the one hand, we will have a passive structure that will consist of aluminium parts manufactured by traditional technologies, let's say, for example, extrusion or die casting. But on top of these parts, we will add some added value functional features by additive manufacturing in order to have a more robust design in terms of crash angle, speed, and so on, and eventually reduce the weight of the structure. And on the other hand, the aim is to integrate also an active system that will somehow allow the structure to adapt for each crash scenario, having a complete robust system. So if we have a look more in detail in the next slide, we can see here on the left side, we have started with the die casting part that we see here, that it's coming from the SALEMA project and that we all know quite well now after the nice presentation of Manel. We have, based on this part, drawn some initial simple extruded profiles, some longitudinal members, and a cross member, a bumper, as we can see here. And the aim now is to combine this passive structure with an active system so that we will have not only actuators, but it will also need to integrate some sensors in order to detect the parameters of the collision, and also some auxiliary elements and control unit and so on. So in the following slide, as we can see here, all the outputs of this project in terms of designs or material modeling, or all the outputs will be validated and tested in full crash simulation. So for this purpose, we will use the GLab G3 model that has been internally developed by Gestamp, that we can see here. And we will simulate three crash scenarios that are based on the three cases previously identified and mentioned. So we will have a first one with a relative angle of 89 degrees between the barrier and the vehicle. Another one with a relative angle of 146 degrees, and a final one with a relative angle of 110 degrees. So this was all from my side. I give you back the floor, Sergi.
Thank you, Andoni, for the nice presentation. And I would like just to complement or add some more information about this ABFF that Andoni mentioned. And this is the current work that we already done in this first work packages, or these first stages of the project. And as you can see here, well, we are working on developing these new aluminium powders with high amount of recycled aluminium, and also with a low content of critical raw materials. Here, once again, we are using part of the knowledge developed in SALEMA project. And right now we have just two materials on the table, and also with some added zirconium in order to enhance somehow the mechanical properties for the laser metal deposition method that you will see later. And here you can see just a picture on how we are producing these aluminum powder particles. and we are using a centrifugal atomization. This, let's say, quite simple to see how it works, but then it's not that simple to produce this powder. So the process is just mainly based on to melt the material and then drop this melted material on a spinning disc that spreads this aluminium alloy, inside the tank, and we are producing these small particles of about 50 to 100 microns that are then used here in the laser metal deposition machine. Here, I think there is another video, and you can see, well, this is the tool or the process that we propose in the project in order to print and to add these small scale 3D structures onto different components of the vehicle. And here right now what we are doing is just developing or trying to see which are the best conditions, the best the parameters to obtain this ABFF. So in order to obtain the best shape or the lower thermal effect in the base material, and the best conditions to obtain these properties, or this ABFF with different shapes and so on. And then once we will have these conditions, the idea is to, as mentioned, to improve the mechanical behavior of these profiles here. For instance, here we just added some pictures from this front part. So here we have this front rail of this part, and we have the front rail without the ABFF, and then we have different kind of ABFF, in this case straight lines with different lengths, but the main idea is try to also use different patterns that you can see some examples here in the right hand side of the slide in order to obtain this behavior that we want to increase the absorbed crash energy, but also to reduce the weight of the vehicle. And of course, since we are developing this new ABFF, these new conditions of the material, we are also working on new tests in order to estimate crashworthiness and durability by considering this. You can see here bending tests, compression, torsion, fatigue, so fracture toughness, a lot of different tests to consider which is the effect of this ABFF. And just to see an example here, you can see in the top the tube without the reinforcement, and then the different ABFFs. And as you can see here, the point is that with this ABFF we can trigger the folding in different points, and we can play on how this front rail will fold. And of course, this have an impact in the absorbed energy. So right now we did just a first approach and a first attempt on proposing just some simple paths, but then it's expected that with the more complex patterns we can obtain even more absorbed energy. And of course, this will have an effect on reducing the passenger injuries and fatalities, since the material will be able to absorb much energy. So thank you all for your attention, and if you have any question, we're happy to answer it. Thank you very much.
So thank you very much, Sergi and Andoni. So it was a really interesting presentation, and I think that we recognize a few elements in terms of a complexity of such projects, where you have bringing together several capabilities, and here you are developing materials, you develop design, develop concepts, tools, and it's also a very nice project to showcase the interaction with sisters projects like the SALEMA. So I'd like to pass on to some of the questions. I think we still have time for, let me check. Well, there's none from the audience, but I think that I have some questions of my own. I think that the first one is, as we've seen with the fatigue for light, there's quite I would say, strong reliance on simulation tools in this project as well. So I'd like to know from your side, what are these, say, current limitations of those tools, or simulation tools, and how this can be, what's perspective of improve them, and whether there's an opportunity of this within this project also to extend their capabilities.
Okay, if I might answer to this question, I think that it's true that we are going to base part of our work in simulation. In fact, part of the work is to improve, the material characterization and so on. We haven't maybe talked too much about the testing phase afterwards, but in the second half of the project, there is a work package dedicated to building prototypes, manufacturing prototypes, and testing these in real crash, not only in simulations, but also in physical testing, to have a correlation between simulation and physical testing, and see if our conclusions are valid.
Okay, so thanks for clarifying that. And then building upon that, I think that since you're mentioning that, so you have a work package for also producing the prototypes, and I think that's going to be quite a huge thing in the project. So could you tell us what have you anticipated the main challenges related to the exploitation of the findings of the project, and scaling up these solutions?
Yeah, maybe I can answer. The main, as you saw, the technology is, we are proposing, as you mentioned, a lot of new technologies and new manufacturing processes that sometimes is not that easy to implement in current producing procedures. But the aim of the project is to at least present all of these new solutions and then find the best way on to implement these strategies that perhaps they are not, or maybe it's not feasible to implement it for all the situations on all the vehicles, but for some point where we really want to add value and that are critical, or we have these critical parts, is where we can implement these new solutions that sometimes are difficult to implement in all the other situations.
Okay, so so that's from me. Thank you very much. If there's no further questions for the audience, I'd like to thank again our speakers, and pass on the floor to Christian now for the conclusion.